All right, let's talk a little bit now about limits in metric spaces, and what we're really trying to do, right, is generalize this idea of a limit where we had a picture like this, where we had our delta down here and our little epsilon window, and we drew things like this, and we all remember these things from, we remember these things from earlier in the semester. We're all over this. Okay, so what we're trying to do is generalize this for a generic metric space, and it's not going to be very different, but we're going to have to just kind of rethink just a couple of the ideas. Well, first one, we should be able to create the definition just like what we'd expect, and that is we had our old definition, and that is the limit as x approaches a of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus a is less than delta, then f of x minus L is less than epsilon. And so this was our old definition. Sorry, I kind of wrote it staggered, but that's because I wanted all of this together on the same line. And you might be able to guess, well, we have our old definition of distance right here and our old definition of distance right here. So what we should probably do is just erase those and replace them with our new definition of distance. And if we do that, we would have our definition that looks like this: rho of x comma a is less than delta, then rho of f of x comma L is less than epsilon. Okay, so this seems like a pretty good definition, but it has one problematic thing, and let's come think just for a moment about one example that might tell you why this is problematic. And let's ask, well, what about the discrete metric that I mentioned last time? This is the metric that a number is equal to 0, a number is equal to 0 if it's equal to itself, and 1 if it's equal to everything else. Well, what if we were taking a function from, I don't know, any set to any other set using this discrete metric? Then what I want you to notice is you can just let delta be any number less than 1. So if delta is 1/2, then this statement is always true, because this doesn't exist. This is the empty set. This is a false statement, and we talked about false statement is vacuously true. So if this is true, then you can prove that if we have a function going from a discrete metric to any other metric space, then the limit at every point is every point, because we get this crazy fact that we can just choose delta small enough that the only point left is a, but a doesn't count because its distance is greater than 0. So there are no points that fall into this category. Okay, well, so how do we get around this? And the way we get around this is by coming up with the definition, and it's what we call a cluster point. And so A is a cluster point of a set X. Similarly, you can have cluster points of sets and things like that. We'll talk about X right now. A is a cluster point X if for all, and they switched to delta here. I kind of think they should have gone epsilon. But anyway, if for all delta greater than 0, the ball radius delta about A has infinitely many points. Has infinitely many points. So we'll say X. Or if we want to talk about a subset, we could talk about E. So if we have a metric space, we can talk about subsets of that metric space, like E. Okay, so if this is the case, this is what we call a cluster point. So let's do it. Let's think through a couple examples of these cluster points. So here's an example. We could think of the set E, which is the set 1 over n, such that n is a natural number, not a real number, such that n is a natural number, and this will be a subset of R with the usual metric. And so if we think about this space, then what do you notice? Well, I would notice that none of the points in E is a cluster point. So none of the 1 over n's is a cluster point. Why is that? Well, because it's a cluster point of E. So it all depends. When you say cluster point, you have to talk about which set you're referring to. And so we're referring to E right now. So none of the 1 over n is a cluster point of E because just take the ball about 1 over n whose size is smaller than 1 over n. So say 1 over 2n or something. Then that ball doesn't have any values of E in it. So what did I do when I did this? Well, we've got 1, 1/2, a third, a fourth. And all I did, oh wait, not 1 over 2n. I have to like do my calculations here. So let's see, so we've got 1 over n and 1 over n plus 1. And I just need to make my ball small enough that 1 over n and 1 over n plus 1 aren't in it. So let's just do 1 over n minus 1 over n plus 1. And that ends up being 1 over n times n plus 1. So that's the size I'm going to make that ball. At any rate, I can make the ball small enough that it doesn't contain either of the points next to it, and therefore it has only the point itself. Oh, I guess I could have used 1 over 2n because that has only a finite number of points as well. It doesn't have infinitely many points. So I guess I didn't lie to you at the beginning, even though I didn't come up with the set that I wanted. Okay, so this set, 1 over n times n plus 1 being the radius of 1 over n, has only one point. Okay, so none of those are a cluster point, but what I will notice is that 0 is a cluster point. And that's just because 0 is the limit of this function. And so if I take any ball of radius delta around the point 0, then every n greater than 1 over delta, xn is contained in, or 1 over n. We're not talking in terms of a sequence then. The 1 over n is contained in that ball. So I have an infinite number of points in the ball. Okay, so this is called a cluster point. And you can kind of see we're going to have connections between cluster points and the ideas of sequences as we kind of move through. Okay, so this set has only a cluster point at the point 0. None of the points in the set itself is a cluster point. If we think of a set like the set 0 to 1 for R with the usual metric, well then every point in the closed set 0, 1 is a cluster point. So notice that if you take any point in 0 to 1, including 0 and 1, you get a cluster point. Let's not stress ourselves out about proving that. And then finally, let's point out that any x in X with the discrete metric is not a cluster point. And so this was the real problem when we tried to think about limits a second ago, and that was that we're trying to talk about convergence with something that was vacuously true, but the problem is that we were dealing with things that didn't have cluster points. So what we'll do is we will just modify our definition just ever so slightly. And the way we'll modify our definition is just by saying let A be a cluster point of x minus a. And I guess we could just say x because a is only a single point, so you couldn't have, you just couldn't still. But let a be a cluster point, then this definition is the correct definition. So you just have to make sure that you're actually clustering, which, by the way, if you're in kind of a normal set, like the Euclidean metric or something like that, then every point in R is a cluster point of the set of R and things like that. So you only have to be careful in a couple of those very basic situations. But now that we have this definition, we can go through and do all the things that we would have normally done with our limits. So, for example, we could come over and prove things like this. The limit as x approaches a of f plus g of x equals the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Oh, there's one issue. The issue is you have to be in a space where this is defined. So we would have to be like in the real numbers or something in order for this to be a reasonable formula. But if it is, then you can do this problem kind of as we would expect. Especially, you know, if the range, if the codomain is the real numbers, then this is perfectly fine. You can prove things like the sequential characterization, and you could do that for any space. So you could prove a bunch of other things, you know, that there's only one limit value and things like that. So all of these things that were true about limits, you can prove them with these new metric spaces. And what do? You go through the old proof and you just replace, where you see the absolute values, you just replace with the distance metric, right? So when you see an absolute value like this, you just replace with rho of x, y, and then everything works out. Like I said, you have to be a little bit careful sometimes, you know, about whether you're allowed to do the operations that you're allowed to do. But generally, this is okay. We also have a definition of continuity, and so continuity looks like this. It looks just like what we would have expected earlier. If for all epsilon greater than 0, there exists a delta greater than 0. And so again, we'll talk about a cluster point here. For all, there exists a delta greater than 0, such that if rho of x minus xa is less than delta, then tau, wait, oh yeah, maybe I forgot to use this. I need to go back and change some things. So sorry, those of you who skipped the last half of my definition. I should have written something very different on the very first slide. Notice, I should not have written rho here. And why is that? Well, the reason is we have two sets. We have a function going from one set to a different set. And these sets don't have to have the same metric. So this metric could be a different metric. So let's give it a different letter. The book likes to use the letter tau. I probably would have chosen sigma because it comes after rho in the Greek alphabet. But let's go ahead and go with tau so we match the book. F of x, f of a is less than epsilon. Okay, sorry about that. Now it's fixed. We just changed that letter ever so slightly. Okay, and then what we see is that continuity is the same thing, except we got rid of that rho must be greater than 0 part. Now, what we're going to find is that in class tomorrow, or the last day that I'll have lectures, we'll have another definition for continuity that I think is a really interesting one and works really, really well in spaces where distance is a little bit harder to get a hold of, and it has to do with talking about open and closed sets and how those behave in relationship to the function. But okay, I'm going to make a third video today, so come back for that, and hopefully it'll be